Okay. Yeah, that's it. Come on, connect. Can you see? What the heck is wrong with this thing? VGA, come on, let's go. Oh, for flip's sake. Ah, here we go. There we go, okay. We are here. You drew this, okay. Now, definition. Is this a word people have heard before? Alternating current. Yeah, do you know what it is? Yeah. How would you describe it? Yeah. Opposite directions, precisely how?
Not really sure how to say it.
Yeah, what do you think you know, Siva? It looks like you might have had an idea. What exactly moves backward? Current, yeah. Alternating current is a current that changes its direction. So alternating current is a current in which the flow of charge reverses direction, whereas a direct current, DC current, the flow of charge is only in one direction. Okay, so if you can write that down, please. Got that? Yeah. Are these words you've heard before? Yeah. Now, with the alternating current, the voltage varies between a min and a max. And as such, it has an average voltage. So, okay, let's have a look here. Come on. Okay. So if we look at the graph here, there's time, and there's voltage. The alternating current goes like this. It increases, decreases, increases, decreases. Okay. We'd like to replace it with an average, because remember in physics we say, you know, if something is changing and you want to do some calculation, a good thing to estimate is the average. Then you can use the average instead. But the question is, what do we use as the average? So if this for example is 200, for example, and this is minus 200, it kind of seems wrong to say the average is 200 plus minus 200 over 2, because that would be equal to 0. So then you're saying there's no voltage, so there's no energy. So that's not quite right. And then you realise, well, you don't actually care that it's minus. The direction doesn't matter. You only care about the size. So really you want to know what's the average of this function, the one that looks like this. So you might say, okay, it's the top plus the bottom divided by 2. And that actually works quite well, but that works really well when it's linear, whereas this is actually a curve shape. So there is a formula for maths that gives you a good average to use for these types of graphs. And it's not the max divided by 2, it's the max divided by square root 2. This actually gives you a better estimate of the average voltage. Okay, I don't know if you've seen that before. No. Got that? Yeah? Continue? So finally, do we have a handy way to figure out which way the induced current will flow? So remember, we had the grip rule for the magnetic field around the current. We had the left-hand rule for the force on a current in a magnetic field. And then we want to know for the generator, is there a way to work out which way the current will flow? And there is, and this is the right-hand rule. So this is the motion, this is the field, and this is the current. If I go back maybe, actually hang on, let me go back to the picture of the generator. I'll show you how it works. So you want to know which way the current will move in your generator, okay? So firstly, you put this finger in the direction of the field, okay, on your right hand. So the field goes from north to south. So I point that way, okay? And then this finger is the force that makes the movement. So if you're turning the wheel around this way, and you want to know which direction the current is moving here, the force is upwards here to make the wheel turn. It's like an up force here. So your thumb is pointing up. This is pointing right. And my fingers are pointing into the board. Okay? So you can see that's why in the diagram the current is going in here. Now let's test it out for this side. Okay? So again, which way is the current going? The current is, the field is still going to the right. Okay? What way is the force on the red side of the generator? What would you say the direction of the force? Down, yeah, because it must be down to make the wheel turn. So you have to put your hand upside down. So the current is flowing to you. And you can see the picture it is. You guys are looking a bit confused. Are we confused?
Just tired.
Tired? Yeah. So we actually have 3 hand rules in total. Right hand grip, Fleming's left hand, and Fleming's right hand. Right hand grip is for one current and the magnetic field it makes. Left hand is to calculate the force. And then the right hand is for calculating the current's direction. Yeah. So again, I think it would be good if you could try and draw it in your notes. Where is my cursor? Where is my cursor? There you go. Fleming's right hand rule. to do in this lesson.
How should we know when to use the right hand?
Good, when to know which one to use. So the left hand, you use it when you're trying to figure out what the force is because a charge is moving in a magnetic field. The right hand you use when you try to figure out what the current is because you're maybe generating power. So it's roughly speaking, Siva, it's like you use the left hand to figure out the force and use the right hand to figure out a current. It's usually what's happening. Okie dokie. You drew that, guys? Siva? Yep. Okay, let's continue. So, let's continue. There. Okay. So, a final little hint before we look at some examples. So, do you remember that formula I gave you earlier? Voltage equals N delta phi over delta T. Remember that? So my little hint here is, normally in the delta phi, either the B or the A changes, but never both. That's a little too difficult. So when you're thinking about what the delta phi is, you need to think about which is changing, the B or the A. So this delta phi is usually either A delta B or B delta A. It's usually one of the two. The delta B is if the B changes, and the delta A is if the A changes. Usually a swept out area. And let me draw that. So I'll give you just a picture to give you an example here. So suppose you have a magnet, and then maybe this is T equals 0, and then this is T equals 1, and then the magnet, you remove it, so it's gone. So this had a magnetic field, north to south, and now there's no magnetic field. So what has changed here? The delta B has changed. Okay, so for example, if this is 1 Tesla and now this is 0 Tesla, the delta B will be 0 minus 1. So minus 1 Tesla. Okay, that's how a B might change. Now, what about how an A might change? So you might think, oh, does the area change means that the shape changes? It's actually not that. You might think it's something like that, but it's something else. So this is what a delta A looks like. So you have a magnet, north, south, and we go from north to south, the magnetic field. And maybe you have a piece of copper here. So this is copper. What's copper? Cu, isn't it? Yeah. So imagine you move the copper wire down here. So it goes from here to here. The delta A is actually this area. It's the area that you draw in space when you move something. So if this is the copper wire, and if I start moving it, I'll get a current inside of it. And the delta A is the area I make per second. Okay? Do you remember I said if you have a conductor and you move a magnet, it makes a current. Or if you don't move the magnet but you move the conductor, it makes a current. So to calculate the voltage, you need to calculate delta A. Delta A is the area you draw as you move the conductor. Because this has no area, it's just a piece of wire, so it's never going to be that. And anyways, even if it was, the area of the wire is not changing. So the delta A is what you would call the swept out area, the area that you draw. Yeah? You don't look happy with this, Matt. You sure? You all look tired. You all look very, very tired, actually. What was happening last night? You all had a party or something? Or no? No, you're just tired? Yeah. Exhausted. You all look exhausted. Okay. And Chow is so tired he's not even here. Right. There is another way we can write the formula BLV, but I don't use it, but they sometimes use it in the exam. You don't actually need to use it, but I just want to show it to you. So I think it's good if you write this little proof down. So this is if the delta B is 0 and the delta A is not 0. So this is like the example I just drew. So an example might be you have a wire of length L and it moves with velocity v, okay, and it's inside a magnetic field. And we want to calculate what voltage do we get here in the wire. So what's the formula? Formula equals N delta B over, delta phi over delta T. Now why do we have the minus here? That's for Lenz's law. So I don't care about the minus, I just want to know how big it is. So I'll just write it as N delta phi over delta T. Now, the N represents the number of loops. So for example, you could have a piece of iron, but then you wrap the wire around it 10 times. So you actually make 10 times more if it's wrapped around 10 times. But if this is just one piece of wire, then the N is 1. Okay, what's changing here? The area or the magnetic field density? It's the area. So because phi equals BA, this becomes B delta A over delta T. Okay so far? Yeah? Now, let's simplify this a little bit more. So equals B delta, okay. Now let's work out the area. So the area is this here. So how big is this side? L. And how big is this side? Well, we could use our distance, speed, time triangle. So this distance here is the speed, which is v, yes, multiplied by the time, which is delta t. So that's how big that piece is. Okay, so that becomes delta A becomes v delta t. L v delta t. The area here is L v delta t. It's that multiplied by that. But of course you can see the delta t's cancel here. So you're left with the formula BLV. So this, and that V is not voltage. Sorry, I'll make that a little bit different, voltage. So the voltage is equal to the magnetic field times the length of the wire times the speed of the wire in the field. So if you'd like, you can use that formula, but that formula is the same as this formula. You can travel from there to there, and this is the little proof. But just to save time, it might be quickest to use this formula, BLV. Did you write the proof down, Andy? That's good. Anybody got plans for next week? Is anyone going to the Galway trip? Oh, great. Anyone else going with you? Oh, wonderful. Are you not going, Andy? No. What about Chow? Is he going? Great. And are you going to stay the night or just the day? just for the day. Yeah. I've been to Galway a couple of times last year. It's really nice. It's a very nice student place, you know. It's not so big, it's not so expensive, lots of things to do and see. It's quite nice. Is anybody thinking of going to Galway? Yeah, oh, very good, okay. This is going to be your first time there? Ah, good. So I hope it leaves a good impression on you then. I forget, what did you say you want to study next year? Biomedical. Oh yeah, Galway's good for that. Yeah. They are very good. Yeah, no, they're good for that. Yeah. Okay, did you all write this down? Yeah. Right. I think there must be time for examples now. Yeah. Okay. So, an insulated copper wire is wrapped around a metal pipe which is 30 centimeters long and 5 centimeters wide. The wire is wrapped around 100 times, and a 1.5 Tesla magnet is moved through the pipe over a time of 3 seconds. What is the average EMF induced through the copper wire? At the moment, the magnet is inside the pipe. Now, I'm sorry, my question is not very clear, so I'll draw a picture. Okay, so you have a pipe, and I wrap a copper wire around it. Okay, and what will happen is I'll measure a voltage. Now, here's the magnet here. Okay, do you remember what Lenz's law said? Which way would the induced current flow as this moves in? The current will flow out this way. So I'll get a voltage here. My question is, how big will that voltage be? So how big is my magnetic field? It's 1.5 Tesla. Okay, and at the moment, how much magnetic field is inside of this? 0. And then what happens in my story? I move it inside. So it's inside the pipe here. Okay, and it takes me, I move it in kind of slowly, it takes me 3 seconds to move it into the pipe. I know I said through the pipe, I should have said into the pipe. What else do we know? The pipe is 30 centimeters long and 5 centimeters wide. So this is 30 centimeters long and this is 5 centimeters wide. What else? Okay. Right, so let's calculate the voltage. Now, again, I don't care about the minus because I know the direction already, so I don't care about the minus. Right, what's the M? It's 100. Delta phi over delta t. Now, what is changing here? The B or the A in the formula phi equals BA? What do you think is the changing thing here? B or A? You got a 50-50 chance. Correct. Yes. So at the very beginning, for the B, you have no Teslas inside, and then after 3 seconds you have 1.5 Teslas inside. So the B is 1.5 minus 0. So that's 1.5. Okay? Now, the A, what's the A here? Now that's maybe tricky. Can anyone see what the area is here? Yeah, actually, yeah, what do you think it is?
No, never mind.
It's not clear. It's not clear. The area is actually like the circle. It's penetrating a circle. The perpendicular area is the circle. Now, you actually, how many of these circles do you have? You have 100 of them. That's why this gets multiplied by 100, because there's actually 100 circles that are being penetrated by the magnetic field. So that's why you multiply by 100. So it's 100 times pi or squared times 1.5 over 3, because, sorry, this here is A times delta B is this thing here on the top. And we worked out the delta B and we can work out the A. Now you see, this isn't easy. This is why I said this topic is hard in the exam. It's not easy because it's quite different to other chapters. So if we type that in, we can get the answer here for the voltage. Yeah? You got an answer on that? What you got?
I don't trust mine, so I'm gonna wait for it.
Okay.
0.098.
Yeah, okay.
0.098 volts then. Got that? Need a second on that?
Yes, yes.
Yeah. Difficult? Maths? What do you think? Tricky? Yeah. Continue? Another example. Okay, so a plane taken off heading towards Santa Claus at the North Pole. The magnetic flux density of the Earth is 0.07 millitesla. The wingspan of the plane is 60 meters and the climbing speed is 250. What's the direction and size of the current in the wings? So, what's happening here is, here's the North Pole, Santa lives there. South Pole, penguins live there. Mecca's over here, and America's over here. Okay, so you have a plane, I'll try and draw it, and it takes off, this is what I say, and it's heading north. So it's heading to the north here. Which way is the magnetic field in this picture? Yeah, so there's a magnetic field going here, like this. Okay. Now, if you were to look at the picture from the side, here's the plane here. This is from the side, okay? And the plane is taken off, so it's heading this way. And this is the North Pole up here. And the magnetic field is going that way. Okay? Which hand do I use here to get the direction? It is the right hand, because I want to know where the current is. Okay? So if I use this one here, which direction is the force? Which direction is the movement? Yeah, well, actually there's two movements, isn't there? There's a movement this way and a movement this way, if you think about the two components. Now what's interesting is you don't actually care about this movement, okay? Because if you look at your fingers, everything must be perpendicular. The movement, the field and the current, they all must be perpendicular, okay? So you actually get no induced current from the movement which is parallel to the field. Only the perpendicular one you care about. So this is like the F here, the movement. So if this is up and the field in my picture here is to the right, then which way will the current move? Into the page. So here on the wings, you're looking at the side, okay? Actually, that's a stupid looking plane. If you're looking at the side, it should be more like this. Sorry. There's my plane. Beautiful. Right, so you have your field this way. What did I say it was? 0.07 millitesla. And you'll have a current that is going into the page here. And the plane moves this way, but you actually do not care about this component, you only care about this component. So there's a upward movement of 250, I tell you. 250 meters per second. And you don't care about this component. You don't care about it. And my question is, what's the current here? So this is an example where you can use the other formula, if you like. The one that, because there's only like one wire, because it's like one wing. It's not like the plane has a wire wrapped around it. So there's one piece of wire, which are the wings, and it's moving with a velocity v. So you can use the formula I gave you, BLV. So in this one here, it would be 0.07 times 10 to the minus 3. The wings are 60 meters wide. So times 60 times 250. So this is how much voltage is induced in the plane wings. What you get there? 1.05 volts. Yeah. That's, that's pretty big. That's enough to power your calculator at least. So that's like free energy, because the voltage is across the plane just because the plane is moving in the Earth's magnetic field. Yeah. Continue. Oh, tell me, when the plane reaches its maximum height, and it's flying at its maximum height, will you still have this voltage or not? What do you think? What do we think? When the plane reaches its maximum height. No, why not? Yeah, but there's no more movement vertically, so there's no more. Basically, the V here has become 0, because you only remember it's only the movement perpendicular to the field that makes the current. Okay, so if you have a field and you have movement perpendicular to it, you can get a current. But if you have a field and you have no movement perpendicular, only parallel, there's no current. Okay. I know this is tricky. I know. It's like the worst answered question in the exam for everybody. Okay, so look, what's the story now? I know these questions are a pain, but you really want to try and be good at them, because even if you don't do it in section B, you have to do it in section A. And the bad news is, I think I told you this before, in the section B of the exam, there's always one more semester 2 question than there is a semester 1 question. They're not balanced 50-50, okay? So that means there'll be 2 of the same type of question in section B. So for example, there could be 2 wave questions. There could be 2 fields questions, or there could be 2 atoms questions. Now, atoms are the best question in the exam because I don't think they're so hard, and because you do chemistry, it kind of feels familiar. So if you get 2 atom questions, then that's a good exam. If you get 2 fields questions, then that's a hard exam. So you need to be prepared for that. Okay? Why don't you try these for a few minutes, and then will we have a tutorial or another lecture? What do we want to do? I'm kind of thinking we might do a tutorial if people have tried. Have people finished the magnetic field questions from last time on page 123? On 123? Did you give them a go on 1, 2, 3? And how did they go? Wait, do we still have to do 1, 2, 1? Yeah, we have to do 1, 2, 1 and 1, 2, 3, don't we? I haven't done those yet. Okay, so I'll tell you what, we'll have a tutorial in a few minutes. We'll go through the answers for 1, 2, 1 and 1, 2, 3. Okay, so we'll just try these for about 10 minutes and then we'll have a double worksheet tutorial.